In 1963, astronomer Martin Schmidt sat at his desk at the California Institute of Technology, staring at a spectrum that made no sense. The object he was studying, a faint point of light called 3C273, had been photographed many times before. It looked like an ordinary star, but its light signature was unlike anything ever recorded. The spectral lines were all wrong. They appeared at wavelengths that corresponded to no known element. For months, Schmidt and his colleagues had tried to match these lines to laboratory measurements. Nothing worked. The data seemed to be telling them something impossible. Then Schmidt had an idea. What if the lines weren't wrong? What if they were simply shifted far beyond what anyone expected? He calculated the redshift and checked his math. Then he checked it again. The number that emerged would change astronomy forever. This small point of light, barely visible in the night sky, was not a star in our galaxy. It was an object nearly 3 billion light years away, shining with the power of 100 trillion suns. It was releasing more energy than every star in our entire Milky Way galaxy combined, from a region smaller than our solar system. The object that Martin Schmidt had just identified would come to be known as a quasar, and it would force scientists to confront a fundamental question. What could possibly generate that much power? The answer would lead to black holes, to the violent hearts of galaxies, to jets of matter, traveling at nearly the speed of light. It would reveal a universe far more extreme, far more energetic, and far more strange than anyone had imagined. This is the story of the brightest objects in existence. The universe contains structures of extraordinary power. Stars fuse atoms in their cores and release enough energy to shine for billions of years. Supernova explosions briefly outshine entire galaxies. Neutron stars pack more mass than our Sun into a sphere the size of a city. But none of these phenomena come close to the energy output of quasars, and there are even more extreme cousins, blazars. A single quasar can emit more light than 1,000 Milky Way galaxies. A blazar can vary in brightness by a factor of 10 in less than a day. These objects are so luminous that they can be seen across most of the observable universe, serving as cosmic lighthouses that mark the locations of the most massive black holes in existence. This documentary will explore how astronomers discovered these extraordinary objects, how they fought to understand what they were seeing, and how decades of research finally revealed the engines that power them. We will begin in the early 20th century, when radio astronomy first opened a new window on the cosmos. We will follow the confusing trail of evidence that led to objects that seemed to violate the laws of physics. We will examine the competing theories that tried to explain them, and see how the correct answer eventually emerged. Along the way, we will learn about the supermassive black holes that lurk at the centers of galaxies. We will understand how matter falling into these black holes releases energy with incredible efficiency. We will see how magnetic fields and rotation create jets of particles that travel at 99% of the speed of light. We will discover why blazars appear even more extreme than quasars, and what this tells us about the geometry of these cosmic engines. We will examine what quasars and blazars reveal about the early universe, about galaxy formation, and about the evolution of cosmic structure. And we will confront the questions that remain unanswered. How did supermassive black holes form so quickly after the Big Bang? What determines which galaxies host active nuclei and which remain quiet? What will happen to these objects as the universe continues to age? The journey ahead covers some of the most extreme physics in nature. It requires us to think about gravity at its most intense, about matter at its most energetic, and about timescales that span the history of the cosmos. Let us begin. For most of human history, astronomy meant looking at visible light. Stars, planets, nebulae, and galaxies all revealed themselves through the same narrow band of electromagnetic radiation that our eyes evolved to detect. This limitation was not merely technical. Scientists knew that other forms of electromagnetic radiation existed. In 1800, William Herschel had discovered infrared radiation by measuring the temperature beyond the red end of the visible spectrum. In 1895, Wilhelm Röntgen had found X-rays. By the early 20th century, the full electromagnetic spectrum had been mapped out, from radio waves with wavelengths measured in meters to gamma rays with wavelengths smaller than atomic nuclei. But knowledge and capability are different things. Detecting these invisible forms of radiation from cosmic sources required technologies that did not yet exist. The breakthrough came accidentally in 1932 at a research laboratory in Holmdel, New Jersey. Karl Jansky, a young physicist working for Bell Telephone Laboratories, was investigating sources of radiostatic that interfered with transatlantic communications. Bell wanted to understand the noise so they could design better equipment. Jansky built a large antenna mounted on a rotating platform. It looked more like a piece of farm equipment than a scientific instrument. The structure was 20 meters long and 4 meters high, constructed from brass pipes and wooden planks. Jansky called it the merry-go-round because it rotated on a set of wheels salvaged from a Model T Ford. For months, Jansky recorded the radio signals his antenna received. He quickly identified two expected sources of interference: nearby thunderstorms and distant thunderstorms. But there was a third signal that puzzled him. It was a steady hiss, always present but varying in intensity throughout the day. At first, Jansky thought this signal might come from the sun. The intensity seemed to follow a daily pattern, but careful measurement revealed that the peak arrived about 4 minutes earlier each day. This is exactly what you would expect from a source fixed among the stars, not from the sun, because Earth's rotation relative to the stars differs from its rotation relative to the sun by about 4 minutes per day. By August 1932, Jansky had traced the source of the mysterious hiss. It came from the direction of the constellation Sagittarius, the center of our Milky Way galaxy. For the first time in human history, someone had detected radio waves from outer space. Jansky published his findings in 1933. The New York Times ran a front-page story with the headline, "New Radio Waves Traced to Center of the Milky Way." Newspapers across the country picked up the story. For a brief moment, the discovery captured public attention. But the scientific community was less impressed. Astronomers in the 1930s were focused on visible light. They had finally settled the question of whether nebulae were objects within our galaxy, or separate island universes far beyond it. They were measuring the expansion of the universe and debating its implications. Radio waves from space seemed like a curiosity, not a priority. Bell Telephone Laboratories was similarly uninterested. They had hired Jansky to solve a practical engineering problem, and he had solved it. The cosmic hiss could not be eliminated, so engineers would simply have to design around it. There was no commercial reason to pursue the discovery further. Jansky himself wanted to build a larger antenna and study the cosmic radio waves in more detail. But his employers assigned him to other projects, and he spent the rest of his career working on problems unrelated to his discovery. He died in 1950 at the age of 44, never returning to the field he had founded. For nearly a decade, only one person in the world actively pursued radio astronomy. Groda Reber was an amateur astronomer and radio engineer living in Wheaton, Illinois. He read about Jansky's discovery and became fascinated. If radio waves were coming from space, what else might be out there? In 1937, Reber built a parabolic radio telescope in his backyard. It was 9 meters in diameter, constructed from sheet metal at a cost of about $2,000, paid from his own pocket. His neighbors thought he was building a water tower or perhaps losing his mind. Reber spent years scanning the sky with his homemade instrument. He produced the first maps of the radio sky, identifying several regions of strong emission beyond the Milky Way's center. He published his results in astrophysical journals, essentially creating the scientific literature of a new field single-handedly. The isolation of these early efforts is remarkable. Jansky had opened a door to a completely new way of observing the universe, but almost no one walked through it. The reasons were partly sociological, as astronomers and radio engineers lived in different professional worlds. The reasons were also practical, as building sensitive radio equipment was expensive and technically demanding. World War II changed everything. The conflict created an urgent need for radar, which operates on the same principles as radio astronomy. Governments poured money into developing radio technology. Engineers learned to build sensitive receivers and large antennas. Radar networks scanned the skies for enemy aircraft. In the process, radar operators sometimes detected unexpected signals. In 1942, British radar stations picked up strong interference that seemed to jam their equipment. Military officials initially suspected German electronic warfare, but physicist James Stanley Hay investigated and traced the source to the Sun, which was experiencing a period of intense solar flare activity. The Sun was emitting powerful radio waves. Hay continued his research after the war, now free to pursue scientific questions. In 1946, he and his colleagues detected radio waves from a region in the constellation Cygnus. This source, later called Cygnus A, was intense and compact. It seemed to come from a specific point in the sky, not from an extended region like the Milky Way center. What was it? The source's position corresponded to no bright visible star or nebula. It seemed to be something new, something that emitted radio waves strongly, but visible light only weakly or not at all. By the late 1940s, radio astronomy had transformed from one man's backyard hobby into a growing international endeavor. Former military radar installations were converted to scientific use. New observatories were founded in England, Australia, the Netherlands, and elsewhere. A generation of physicists and engineers who had spent the war years developing radio technology now turned their skills to peaceful purposes. These early radio astronomers quickly discovered that the sky looked very different at radio wavelengths than at optical wavelengths. The Milky Way glowed brightly, produced by energetic electrons spiraling through the galaxy's magnetic field. The Sun was a radio source, especially during flares, but there were also many discrete sources scattered across the sky with no obvious connection to visible objects. Cataloging these sources became a priority. Astronomers at Cambridge University in England began systematic surveys using a technique called aperture synthesis, which combined signals from multiple antennas to achieve higher resolution. These surveys assigned numbers to radio sources based on their coordinates and brightness. The third Cambridge catalogue, published in 1959 and revised in 1962, listed over 400 sources. Many would later prove to be among the most interesting objects in the universe. They were given names like 3C48, 3C147, 3C273, and 3C279. At the time, no one knew what most of them were. The identification of radio sources with visible objects proceeded slowly. Radio telescopes of that era had poor angular resolution. They could detect that a source existed in a particular part of the sky, but could not pinpoint its exact location with the precision needed to match it to a specific star or galaxy. This problem was partly geometric. The resolution of any telescope depends on its size relative to the wavelength of light it detects. Radio waves have wavelengths millions of times longer than visible light. To achieve the same resolution as a modest optical telescope, a radio telescope would need to be hundreds of kilometers across. Building such a structure was impossible, but astronomers found clever workarounds. Cyril Hazard at the University of Sydney realized that the moon could help. As the moon moves across the sky, it occasionally passes in front of radio sources, temporarily blocking their signals. By timing exactly when a source disappeared and reappeared behind the moon's edge, astronomers could calculate its position with much greater precision than their telescopes alone could achieve. In 1962, Hazard and his colleagues used this lunar occultation technique to pin down the location of 3C273. They determined its position to within about 1 arcsecond, precise enough to identify it with a visible object. The result was unexpected. The radio source coincided with what appeared to be a faint blue star. This was strange. Why would an ordinary star be such a powerful radio emitter? And if it was a star in our own galaxy, why had it not been noticed before? Optical astronomers pointed their telescopes at 3C273 and took spectra. What they found made no sense at all. A spectrum is one of the most powerful tools in astronomy. When light from an object passes through a prism or diffraction grating, it spreads out into its component colors. Each chemical element absorbs and emits light at specific wavelengths, creating a pattern of bright and dark lines that acts like a fingerprint. By analyzing these lines, astronomers can determine what an object is made of, how hot it is, and how fast it is moving. The spectrum of 3C273 displayed several bright emission lines. This was not unusual for certain types of stars, but the wavelengths of these lines did not match any known element. They appeared at positions that had no interpretation. Martin Schmidt, a Dutch astronomer working at Caltech, stared at this spectrum for weeks. He tried every combination of elements he could think of. Nothing worked. The data seemed to be nonsense. Then, on February 5th, 1963, Schmidt had his breakthrough. He realized that the mysterious lines were not from unknown elements. They were the familiar spectral lines of hydrogen, but shifted enormously toward the red end of the spectrum. Redshift is a consequence of the Doppler effect. When a source of light moves away from an observer, the wavelengths of its light are stretched, shifting toward longer, redder wavelengths. The faster the recession, the greater the shift. Astronomers routinely measured redshifts for galaxies. Edwin Hubble had used them to discover the expansion of the universe. But the redshifts of galaxies in the 1960s were typically quite small, a few percent at most. The redshift of 3C273 was 0.158. Its spectral lines had been shifted by about 16%. This meant the object was receding at about 15% of the speed of light. According to Hubble's law, which relates recession velocity to distance in an expanding universe, this implied that 3C273 was roughly 2 billion light-years away. It was not a star in our galaxy. It was an object at cosmological distance. But this created an enormous problem. For 3C273 to appear as bright as it did from such an immense distance, it had to be radiating with incredible power. Schmidt calculated that its luminosity was about 100 times greater than our entire Milky Way galaxy, which contains 200 billion stars. The result seemed impossible. No known physical process could generate that much energy from what appeared to be a point source. Within weeks, other astronomers examined the spectra of similar objects. Jesse Greenstein and Thomas Matthews at Caltech found that 3C48 had an even higher redshift of 0.3611, placing it further away and making it even more luminous. The optical astronomer Alan Sandage had been studying these radio stars for years and had classified 3C48 as a peculiar blue star in 1960. Now its true nature was becoming clear. The term quasar entered the astronomical vocabulary. It was short for quasi-stellar radio source, reflecting the fact that these objects looked like stars, but clearly were not. Later, astronomers discovered that many similar objects were not strong radio sources, leading to the alternative term quasi-stellar object, or QSO. The discovery sparked immediate controversy. Some astronomers simply refused to believe the redshift interpretation. If these objects were really at cosmological distances, their energy output violated everything physicists thought they understood about matter and energy. Alternative explanations proliferated. Perhaps quasars were not distant at all. Perhaps their redshifts had some other origin that did not indicate velocity and distance. One proposal suggested that quasars were objects ejected from galaxies at near light speeds. If they were relatively nearby, but moving away from us very quickly, they would show large redshifts without requiring enormous luminosities. This local hypothesis avoided the energy problem, but created new ones. Where were the corresponding objects moving toward us, which would show blue shifts? Why were quasars associated with faint galaxies that showed the same redshifts? Another proposal invoked gravitational redshift. Light escaping from a strong gravitational field loses energy and shifts toward the red. Perhaps quasars were extremely dense objects, not particularly distant, but massive enough to produce large gravitational redshifts. The physics of this idea was sound, but the numbers did not work, An object dense enough to produce the observed redshift would be so compact that it would be a black hole from which no light could escape at all. A few astronomers proposed tired light hypotheses, suggesting that light lost energy as it traveled through space, producing redshifts without any recession velocity. But these ideas conflicted with other well-established physics and could not explain the specific relationships between quasar properties. The debate was sometimes acrimonious. Astronomer Holton Upp spent decades arguing that quasars were not at cosmological distances, pointing to apparent associations between high redshift quasars and low redshift galaxies. He suggested that redshifts might have intrinsic components not related to velocity at all. The mainstream astronomical community found his evidence unpersuasive, but the controversy continued into the 1990s. Meanwhile, the case for the standard interpretation grew stronger. Astronomers found more and more quasars, pushing the redshift record ever higher. They discovered quasars at redshifts of 2, then 3, then 4, corresponding to distances where we were seeing light emitted when the universe was only a few billion years old. The number of quasars peaked at around redshift 2, then declined at higher redshifts. This pattern made sense if quasars were a phenomenon associated with young galaxies, more common in the early universe than today. It was hard to explain if quasars were local objects with non-cosmological redshifts. Observers also began detecting faint galaxies surrounding bright quasars. These host galaxies had the same redshifts as the quasars themselves, confirming that both were at the same distance. The quasars were clearly located at the centers of distant galaxies. Absorption lines in quasar spectra provided additional evidence. Light from a distant quasar passes through clouds of gas between the quasar and Earth. Each cloud absorbs light at specific wavelengths, creating a series of absorption lines. The pattern of these lines revealed hydrogen clouds at multiple redshifts, each corresponding to a different distance along the line of sight. This was exactly what you would expect if quasars were at cosmological distances, with many intervening gas clouds between them and us. By the 1980s, the cosmological interpretation of quasar redshifts was firmly established. These objects really were at immense distances. They really were radiating with the power of hundreds of galaxies. The question was no longer whether this was true, but how it was possible. Understanding why quasars pose such an extreme energy problem requires appreciating the numbers involved. Our Sun is a fairly typical star. It converts about 4 million tons of hydrogen into helium every second through nuclear fusion. This releases energy at a rate of about 400 trillion watts. The Sun has been doing this for 4.6 billion years and will continue for about 5 billion more before exhausting its hydrogen fuel. A large galaxy like the Milky Way contains several hundred billion stars. Their combined luminosity is roughly 10 billion times the Sun's output. This represents an enormous amount of energy production, distributed across a disk 100,000 light-years in diameter. A typical quasar outshines the Milky Way by a factor of 100 or more. Some of the brightest quasars produce 1,000 times more light than our entire galaxy. All of this energy comes from a region so small that it appears as a point source even in our best telescopes. How small? The variability of quasars provides a crucial clue. Astronomers noticed early on that quasar brightness could change by large amounts over short timescales. Some quasars varied significantly within weeks or days. A few showed detectable changes in hours. This rapid variability places a strict upper limit on the size of the emitting region. Consider an object that changes brightness significantly in one day. Light travels about 26 billion kilometers in one day. If the emitting region were much larger than this, different parts of it would be at different distances from us. Their light would arrive at different times, smoothing out any rapid variations. The fact that quasars can vary in brightness on timescales of days or less means that most of their energy must come from a region no more than a few light days across. This is tiny by astronomical standards, smaller than our solar system. Now consider the energy requirements. A bright quasar produces about 10 trillion times the Sun's luminosity from a region roughly the size of our solar system. If this energy came from nuclear fusion, like in stars, the quasar would have to contain fuel equivalent to hundreds of billions of stars packed into a minuscule volume. The fuel consumption would be staggering. At the observed luminosity, a quasar would burn through the mass of our Sun in just a few hours. To shine for millions of years, it would require a fuel supply equivalent to billions of solar masses. Where could such fuel come from? And how could it be converted to energy so efficiently in such a small region? Nuclear fusion, the process that powers stars, converts mass to energy with an efficiency of about 0.7%. For every kilogram of hydrogen converted to helium, about 0.007 kilograms becomes energy according to Einstein's equation E equals mc squared. This efficiency was not high enough to explain quasars. The mass consumption required to produce the observed luminosity through fusion would quickly exceed any reasonable fuel supply. Scientists needed a more efficient engine. By the mid-1960s, some had begun to consider an idea that seemed almost science fiction: black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They form when massive objects collapse under their own weight, compressing matter into an infinitely dense point called a singularity. The boundary around this point, beyond which escape is impossible, is called the event horizon. Black holes had been predicted by Einstein's general theory of relativity as early as 1916, when Carl Schwarzschild found a mathematical solution describing their properties. But for decades, most physicists considered them theoretical curiosities, not real objects. The relevant physics for quasars is what happens to matter near a black hole, before it crosses the event horizon. Matter falling toward a black hole does not simply plunge straight in. Instead, it typically has some angular momentum, some sideways motion that causes it to orbit the black hole. As more matter falls in, it collides with matter already in orbit. These collisions redistribute angular momentum, allowing some material to drift closer to the black hole, while other material moves outward. The result is a flattened disk of spiraling matter called an accretion disk. Within this disk, friction between adjacent layers moving at different speeds heats the material to enormous temperatures. Close to the black hole, where the gravitational field is strongest and orbital speeds are highest, temperatures can reach millions of degrees. At these temperatures, matter glows brilliantly in X-rays and ultraviolet light. The critical insight is the efficiency of this process. When matter falls into a black hole, it loses gravitational potential energy. This energy has to go somewhere. In an accretion disk, much of it is converted to radiation. The efficiency depends on how close matter can orbit before finally plunging in. For a non-rotating black hole, the innermost stable orbit is at 3 times the Schwarzschild radius. Material spiraling in from large distances to this point converts about 6% of its rest mass to energy. For a rapidly rotating black hole, the innermost stable orbit is much closer in. The efficiency can approach 40% for matter orbiting in the same direction as the black hole's spin. Compare this to nuclear fusion's 0.7% efficiency. Gravitational accretion onto a black hole can convert mass to energy about 10 to 50 times more efficiently than stars. This was exactly what quasars required. The idea crystallized in 1964 when Edwin Salpeter and independently Yakov Zeldovich proposed that quasars were powered by matter falling onto massive compact objects. They did not yet specify that these objects had to be black holes specifically, but the connection was natural. Donald Lynden Bell at Cambridge developed the picture further in 1969. He argued that quasars were supermassive black holes at the centers of galaxies, accreting matter from their surroundings. The extreme luminosity came from the gravitational energy released as matter spiraled inward. The small size of the emitting region corresponded to the tiny inner portions of the accretion disk. Lynden Bell's model also explained a puzzling observation. Many galaxies showed unusual activity at their centers without being as extreme as quasars. Some had bright compact nuclei. Others showed unusual spectra with emission lines from highly ionized gas. These active galactic nuclei seem like weaker versions of the quasar phenomenon. Perhaps, Lynden Bell suggested, all large galaxies contain supermassive black holes at their centers. When these black holes were actively accreting matter, the galaxy appeared as a quasar or active nucleus. When the fuel supply ran out, the black hole became dormant and the galaxy appeared normal. This picture implied something remarkable about our own Milky Way. If supermassive black holes were ubiquitous, there should be one at our galaxy's center too. It would be dormant now, not actively accreting much matter, but it should still be detectable through its gravitational influence on nearby stars. We will return to this prediction later. For now, the essential point is that by the early 1970s, the basic mechanism for quasar energy production was understood. Matter falling onto supermassive black holes could release energy with the efficiency needed to explain the observed luminosities. The accretion disk naturally produced light across a broad range of wavelengths. The small size of the inner disk explained the rapid variability, but significant questions remained. How massive were these black holes? How did matter get close enough to fall in? What produced the powerful radio emission that had led to the discovery of quasars in the first place? Black holes come in different sizes. The smallest known are stellar mass black holes, formed when massive stars exhaust their nuclear fuel and collapse. These typically contain between 5 and 30 times the mass of our Sun, with event horizons only tens of kilometers across. The black holes that power quasars are vastly larger. They contain millions to billions of solar masses, and their event horizons span distances comparable to our entire solar system. These are called supermassive black holes. The distinction matters because the physical conditions near a black hole depend strongly on its mass. Counterintuitively, the environment near a supermassive black hole is actually less violent than near a stellar mass black hole. The reason involves the concept of tidal forces. When an object approaches a black hole, the gravitational pull on its near side is stronger than on its far side. This difference creates a stretching force that can tear objects apart. For a stellar mass black hole, this stretching becomes extreme well outside the event horizon. An object would be torn to pieces long before reaching the point of no return. But for a supermassive black hole, the event horizon is so large that tidal forces at its surface are relatively gentle. An astronaut falling into a billion solar mass black hole would cross the event horizon without experiencing any unusual physical stress. The lethal tidal forces would only become significant much later, deep inside the black hole. This has important consequences for accretion physics. Matter can approach a supermassive black hole and form a stable disk at distances where a stellar mass black hole would already be tearing it apart. The accretion process can proceed in a relatively steady, organized manner. How much mass do quasar black holes actually contain? Several methods have been developed to estimate this. One approach uses the relationship between luminosity and mass known as the Eddington limit. When matter falls onto a black hole, the resulting radiation exerts an outward pressure on incoming material. If the luminosity is too high, this radiation pressure can actually halt the infall, cutting off the fuel supply. The maximum luminosity at which accretion can proceed is called the Eddington luminosity. It depends directly on the black hole mass. More massive black holes have higher Eddington limits because their stronger gravity can overcome greater radiation pressure. If a quasar is shining at its Eddington limit, its luminosity directly tells you its mass. In practice, quasars probably operate somewhat below this limit, but the relationship still provides a useful estimate. For the brightest quasars with luminosities a trillion times the Sun, the implied black hole masses are billions of solar masses. Even typical quasars require black holes of at least hundreds of millions of solar masses. A more direct method uses the technique called reverberation mapping. The idea exploits the fact that light from the hot inner disk illuminates gas clouds farther out. These clouds absorb the disk's light and re-emit it at different wavelengths, producing the bright emission lines visible in quasar spectra. When the disk's brightness changes, the cloud's response is delayed by the time it takes light to travel from the disk to the clouds. By measuring how quickly the emission lines respond to changes in the continuum brightness, astronomers can determine the size of the emitting region. Combining this size with the velocities of the gas clouds measured from the width of the emission lines allows calculation of the central mass. Broader lines indicate faster moving gas, which implies a larger enclosed mass. Reverberation mapping has been applied to hundreds of quasars. The results confirm that supermassive black holes with masses of millions to billions of solar masses are universal features of these objects. A third approach involves direct dynamical measurements of stars and gas near the black holes in relatively nearby galaxies. While we cannot see the black hole itself, we can observe the orbits of objects influenced by its gravity. The most dramatic example is our own Milky Way galaxy. For over 20 years, astronomers have tracked the motions of stars orbiting the galaxy's central region. The star, called S2, completes one orbit in just 16 years, approaching within 17 light hours of the central object at closest passage. Its orbital speed at this point exceeds 7,600 kilometers per second, about 2.5% of the speed of light. The mass required to hold S2 in this orbit is about 4 million solar masses, confined to a region smaller than our solar system. No known configuration of stars or other matter could achieve this density without collapsing to a black hole. This remains the most direct evidence that supermassive black holes are real objects. Similar measurements in other galaxies have revealed supermassive black holes with masses ranging from a few 100,000 to tens of billions of solar masses. The record holder, discovered in 2011, is the black hole at the center of the galaxy NGC 1277, which may contain 17 billion solar masses. These direct measurements reveal an important relationship. The mass of a galaxy's central black hole correlates strongly with the properties of the galaxy's central bulge of stars. More massive bulges host more massive black holes, following a ratio of roughly 1 to 1,000. This correlation suggests that black holes and galaxies grow together, each influencing the other's development. The energy released by accreting black holes may limit star formation in their host galaxies, while the supply of gas available for both processes may be controlled by larger-scale cosmic structure. How do supermassive black holes form in the first place? This remains an active area of research. One pathway begins with the stellar mass black holes left behind when massive stars die. If these black holes merge with each other and accrete surrounding gas, they could gradually grow to supermassive scales. But there is a problem. The earliest quasars are observed at redshifts beyond 7, corresponding to times less than 800 million years after the Big Bang. For a black hole to reach 1 billion solar masses by this time through ordinary accretion, it would have to grow very quickly, operating near the Eddington limit almost continuously from a very early starting point. This is possible but challenging. It requires black hole seeds that formed very early and grew very efficiently. The seeds themselves might have been the remnants of the first generation of stars, which theoretical models suggest could have been much more massive than stars today. An alternative is direct collapse. In the very early universe, under the right conditions, a massive cloud of primordial gas might collapse directly to a black hole without first forming stars. This could create seeds of tens of thousands of solar masses, giving a significant head start on the growth to supermassive scales. Distinguishing between these scenarios is difficult because we cannot observe the formation process directly. The black holes we see today are the survivors, and reconstructing their histories requires theoretical modeling combined with observations of ever earlier epochs. What we can say with confidence is that supermassive black holes are not rare. Detailed surveys suggest that essentially every large galaxy contains one. Many of these black holes are dormant today, accreting little material and radiating weakly. But the presence of quasars in the early universe tells us that most of these black holes went through active phases in their past. The lifetime of quasar activity is uncertain, but probably measured in tens to hundreds of millions of years, a brief episode in the billion-year history of a galaxy. During this time, the central black hole shines brilliantly, outshining all the galaxy's stars combined. Then the fuel runs out, the accretion disk fades, and the black hole falls silent. This episodic activity may occur multiple times in a galaxy's life, triggered by events that supply fresh gas to the central regions. Galaxy mergers are one obvious mechanism. When two galaxies collide, the gas is stirred up and driven toward their centers, where the black holes can accrete it. The picture that emerges is one of dynamic interaction between black holes and their host galaxies. The black holes grow by consuming gas, releasing energy that can affect the entire galaxy. The galaxy supplies the black hole with fuel, determining when it is active and when it is quiet. Together they evolve over cosmic time, their fates inextricably linked. The fundamental mechanism of quasar energy production is gravitational accretion. Matter falls toward the central black hole, converting gravitational potential energy to radiation along the way. But the details of how this happens involve some of the most complex physics in astrophysics. The accretion disk forms because infalling matter has angular momentum. Gas clouds in a galaxy do not simply fall straight toward the center. They orbit the galaxy's mass, moving on curved paths. When they encounter other gas or lose energy through radiation, they spiral inward, but they retain their angular momentum. This angular momentum prevents matter from plunging directly into the black hole. Instead, it forms a rotating disk that extends from close to the event horizon out to distances of perhaps light years. Within this disk, adjacent rings of material orbit at different speeds, with inner material moving faster than outer material. The friction between these layers does two important things. First, it transports angular momentum outward, allowing matter in the inner disk to spiral ever closer to the black hole. Second, it converts orbital energy to heat, raising the temperature of the disk material. The physics of this friction, called viscosity, is surprisingly subtle. Ordinary molecular viscosity, the kind that makes honey flow slowly compared to water, is far too weak to explain the observed behavior of accretion disks. Some additional mechanism must be at work. The leading candidate is magnetic turbulence. Accretion disks are made of ionized gas, which conducts electricity and interacts with magnetic fields. In 1991, Stephen Balbus and John Hawley showed that a weak magnetic field threading an accretion disk becomes unstable and generates turbulent motions. This magnetorotational instability, as it is called, effectively acts as a strong viscosity, enabling angular momentum transport and energy dissipation. The temperature of the disk varies with distance from the black hole. Close in, where gravity is strongest and orbital speeds are highest, temperatures can exceed 1,000,000 degrees Kelvin. At these temperatures, matter emits most of its radiation as X-rays. Further out, temperatures are lower. At a few 100 million kilometers from the black hole, temperatures might be tens of thousands of degrees, producing ultraviolet and visible light. At larger distances still, the disk cools enough to emit primarily infrared radiation. This temperature gradient means that an accretion disk radiates across a broad range of wavelengths. The overall spectrum is characteristic, rising toward shorter wavelengths and then turning over at the highest energies. Observations of quasar spectra match this prediction reasonably well, providing evidence that the accretion disk model is correct. But the picture becomes more complicated when we consider what happens very close to the black hole. General relativity predicts that there is an innermost stable circular orbit around a black hole. Inside this radius, stable orbits do not exist. Any matter that drifts inside this boundary will inevitably fall into the black hole within a short time. For a non-rotating black hole, the innermost stable orbit is at 3 times the Schwarzschild radius. For a maximally rotating black hole, it can be as close as half the Schwarzschild radius, almost touching the event horizon. The location of this inner edge determines the maximum efficiency of the accretion process. Matter releases gravitational energy as it spirals from large distances down to the innermost stable orbit. The closer this orbit is to the event horizon, the more energy is released. This is why rapidly rotating black holes are more efficient engines. Their innermost stable orbits are closer to the event horizon, allowing matter to release more of its gravitational potential energy before disappearing into the black hole. Observational evidence suggests that many quasar black holes are indeed rapidly rotating. Detailed X-ray spectroscopy can reveal the signatures of matter very close to the event horizon, where gravitational effects distort the emitted radiation in characteristic ways. These measurements indicate that the accretion disks extend down to very small radii, consistent with rapid spin. How do black holes become rapidly rotating? They gain angular momentum from the material they accrete. If this material consistently spirals in from one direction, as it would from an organized accretion disk, it adds its angular momentum to the black hole. Over time, as the black hole consumes millions of solar masses of material, it spins up to near maximum rotation. The energetics of quasar accretion are staggering. A typical bright quasar accretes about 1 to 10 solar masses of material per year. This sounds modest compared to the 100 million solar mass black hole doing the accreting, but the energy released is enormous. Converting one solar mass to energy at 10% efficiency yields about 2 times 10 to the 47th power joules, comparable to the total energy output of the Sun over its entire 10 billion year lifetime. A quasar accreting 10 solar masses per year releases this amount of energy every few weeks. Not all of this energy becomes visible light. Some is emitted as X-rays, some as ultraviolet radiation, some as infrared from dust heated by the disk. Some may be carried away by winds of material blown off the disk by radiation pressure. And some goes into the mysterious phenomenon that first drew attention to these objects, the radio jets. When quasars were first discovered, their defining characteristic was strong radio emission. This radio emission does not come from the accretion disk. It comes from something far more exotic, jets of material ejected from the immediate vicinity of the black hole at nearly the speed of light. These jets are among the most remarkable structures in the universe. They can extend for hundreds of thousands of light years, far beyond the boundaries of their host galaxies. They maintain their coherence over distances millions of times greater than their starting diameter. They carry more power than entire galaxies produce from their stars. Understanding how jets form and maintain themselves has been one of the great challenges of modern astrophysics. The basic observation is straightforward. Many quasars and active galactic nuclei show radio emission extending in two opposite directions from the central source. High-resolution radio mapping reveals that this emission comes from narrow channels of material flowing outward at extreme velocities. The evidence for relativistic speeds comes from several observations. The most direct is apparent superluminal motion, where features in the jet appear to move across the sky faster than the speed of light. This sounds impossible, and in a sense, it is. Nothing actually moves faster than light. But when an object moves toward you at nearly the speed of light, at a small angle to your line of sight, geometrical effects can make its apparent transverse speed exceed the actual speed of light. Consider a jet pointing almost, but not quite, toward Earth. Material ejected from the black hole moves at 99% of the speed of light. Over the course of a year, this material travels a certain distance along the jet. But because the jet is pointing toward us, the light emitted at the end of the year's journey has much less far to travel to reach Earth than the light emitted at the beginning. The result is that the year of actual travel appears compressed into a shorter interval of observed time. The material seems to move faster than it actually did. For the right combination of jet speed and angle, the apparent velocity can exceed the speed of light by a factor of 10 or more. Observations of apparent superluminal motion are common in quasar and blazar jets. They provide direct evidence that the jet material is moving at relativistic speeds, typically 95 to 99.9% of the speed of light. What could accelerate material to such extreme velocities? The answer involves the interaction between the black hole, the accretion disk, and magnetic fields. The plasma in and around the accretion disk is highly conductive, and magnetic field lines become frozen into it. As the disk rotates, it drags the field lines around, winding them up like spaghetti on a fork. This winding concentrates magnetic field strength near the rotation axis. The magnetic pressure along the axis becomes very high, creating a channel through which material can be expelled. The rotating magnetic field acts like a giant electromagnetic accelerator, converting rotational energy into the kinetic energy of outflowing material. The detailed physics is described by the field of magnetohydrodynamics, which treats plasma as a conducting fluid coupled to electromagnetic fields. Simulations of black hole accretion in 3 dimensions, first achieved in the early 2000s, show that jets form naturally from this process under the right conditions. The energy source for the jets is controversial. Some models suggest that the jets tap the rotational energy of the accretion disk. Others propose that they extract energy directly from the spin of the black hole itself through a mechanism proposed by Roger Blanford and Roman Znajek in 1977. The Blanford-Znajek process is particularly remarkable. A spinning black hole drags space-time around with it, an effect called frame dragging. Magnetic field lines threading the event horizon are twisted by this rotation. This twisting transmits energy outward along the field lines, powering the jet even without any material flowing into the black hole. In principle, a rapidly spinning black hole could power a jet for hundreds of millions of years by gradually spinning down. The rotational energy of a billion solar mass black hole spinning at near maximum rate is about 10 to the 55th power joules, enough to power a typical quasar for the duration of its active phase. Whether the jets are powered by the disk, the black hole spin, or some combination remains an active research question. What is clear is that the magnetic field plays an essential role in launching and collimating the jets. Once launched, the jets must maintain their narrow structure over enormous distances. This too involves magnetic fields. The jet material is a magnetized plasma, and the magnetic field helps confine it against the tendency to spread sideways. The extreme forward momentum of the relativistic flow also helps maintain coherence. As the jets propagate outward, they eventually encounter the diffuse gas that surrounds their host galaxies. This interaction decelerates the jets and causes them to spread out, forming large radio-emitting lobes. These lobes can be even more extensive than the jets themselves, spanning millions of light years and containing vast amounts of energy. The energy deposited into these lobes comes ultimately from the central black hole. Over time, as the jets transport energy outward, they heat the surrounding gas and may prevent it from cooling and forming stars. This jet feedback is thought to play an important role in regulating galaxy growth, particularly in the most massive galaxies. Not all quasars have powerful jets. In fact, only about 10% of quasars are strong radio sources, sometimes called radio-loud quasars. The remaining 90%, called radio-quiet, have weak or absent jets despite having similar accretion disks and central black holes. What determines whether a quasar produces powerful jets? This remains poorly understood. Jet production seems to correlate with black hole spin, with more rapidly rotating black holes producing stronger jets. It may also depend on the structure of the magnetic field in the accretion disk or on the properties of the host galaxy. The distinction between radio-loud and radio-quiet quasars may be a matter of degree rather than a fundamental difference. Even radio-quiet quasars show some evidence of weak outflows, and the boundary between the two categories is not sharp. What is certain is that when jets are present, they dominate the radio emission from quasars and create some of the most dramatic structures in the universe. Among the most extreme objects in the universe are the blazars. These are quasars whose jets happen to point almost directly at Earth. The consequences of this geometry are profound. When we look down the barrel of a relativistic jet, everything about it appears enhanced. The light is brighter, the variations are faster, the energies are higher. What was already an extreme phenomenon becomes even more so. The physics behind this enhancement is called relativistic beaming or Doppler boosting. When a source of light moves toward you at a significant fraction of the speed of light, several effects combine to dramatically increase its apparent brightness. First, there is the familiar Doppler effect. Light from an approaching source is blue shifted, meaning its frequency increases. For a source moving at relativistic speeds, this shift can be substantial. Second, there is time dilation. Events in the jet appear to happen faster than they actually do because the jet is moving toward us and each successive light signal has less distance to travel. This compresses the observed variability timescale. Third, and most important, there is the beaming of radiation. Light emitted by a relativistic source is concentrated in the forward direction. Instead of radiating equally in all directions, the source projects most of its light into a narrow cone pointing in the direction of motion. These effects combine multiplicatively. For a jet moving at 99.5% of the speed of light, pointing within a few degrees of our line of sight, the apparent brightness can be enhanced by factors of hundreds to thousands. The first blazars were identified in the late 1960s and early 1970s, though they were not recognized as a distinct class until later. The prototypical blazar is BL Lacertae, an object in the constellation Lacerta that was originally classified as a variable star. BL Lacertae's variability was unusual for a star. It changed brightness erratically on timescales of days to hours. With no periodic pattern, its spectrum was almost featureless, lacking the emission or absorption lines typical of stars. In 1968, radio observations revealed that BL Lacertae was a compact radio source, not a star at all. The connection to quasars became clearer in the 1970s. Objects like BL Lacertae seemed to be related to quasars, but with their emission dominated by a different component. That component was the jet, now understood to be pointing almost directly at us. Today, blazars are formally defined as active galactic nuclei, with jets aligned within about 15 degrees of our line of sight. They are subdivided into two categories based on their optical spectra. BL Lacertae objects, or BL LACs, have essentially featureless spectra. The emission from the jet is so bright that it overwhelms any emission lines from surrounding gas. This makes measuring their distances challenging, as redshifts typically rely on spectral lines. Flat spectrum radio quasars, or FSRQs, do show emission lines, indicating that their jets are somewhat less dominant or pointed slightly away from our exact line of sight. They tend to be more luminous and at higher redshifts than BL LACs. The most distinctive properties of blazars arise from their extreme variability. Because we are looking down the jet, small changes in the jet's properties are amplified into large changes in observed brightness. Some blazars vary by a factor of 2 in brightness within a single night. A few have shown changes detectable on timescales of minutes. The most extreme case, the blazar PKS 20155-304, underwent a major flare in 2006, during which its gamma-ray brightness doubled in just 5 minutes. This implies that the emitting region is extraordinarily compact. To vary on timescales of minutes, the emitting region must be no more than a few light minutes across. This is smaller than our solar system, yet the luminosity during the flare exceeded 10 to the 45th power watts, a trillion times the sun's output. Blazars emit radiation across the entire electromagnetic spectrum, from radio waves to the highest energy gamma rays ever detected from astronomical sources. This broad spectral coverage reflects the extreme conditions in the jet. The radio and infrared emission comes from electrons spiraling in magnetic fields, a process called synchrotron radiation. The electrons are accelerated to enormous energies, traveling at 99.99999% of the speed of light. In the jet's magnetic field, they emit radiation across a wide range of wavelengths. The X-ray and gamma-ray emission has multiple origins. Some comes from synchrotron radiation by the most energetic electrons. Some comes from a process called inverse Compton scattering, where energetic electrons collide with lower energy photons and boost them to much higher energies. The photons involved in inverse Compton scattering can come from several sources: the synchrotron radiation itself, light from the accretion disk, or radiation from gas clouds outside the jet. Different blazars seem to have different dominant photon sources, leading to variations in their spectral properties. The most energetic gamma rays from blazars have been detected by ground-based telescopes that observe the faint flashes of light produced when gamma rays hit Earth's atmosphere. These gamma rays have energies exceeding 1 trillion electron volts, far beyond what any human-built accelerator can produce. The detection of such high-energy gamma rays from blazars creates a puzzle. Gamma rays of this energy should interact with lower energy photons in the jet and annihilate, producing electron-positron pairs. The fact that we observe these gamma rays means they must be produced in regions where this annihilation is minimized, perhaps far from the central engine where photon densities are lower. Blazars are rare compared to ordinary quasars, which makes sense geometrically. If jets are roughly cone-shaped with opening angles of a few degrees, only a small fraction of quasars will have jets pointing toward Earth. For every blazar we observe, there should be hundreds of quasars with similar intrinsic properties, but jets pointing in other directions. This geometric relationship has been confirmed observationally. The properties of blazars, when corrected for relativistic beaming effects, are consistent with them being the aligned versions of ordinary radio-loud quasars. The study of blazars provides a unique window into jet physics. Because we are looking along the jet axis, we can probe conditions in the jet interior that would be hidden from view in an off-axis source. Rapid variability allows us to study how the jet changes on short timescales. Multi-wavelength observations reveal how different emission components interact. Blazars have also been the targets of neutrino searches. In 2017, the IceCube Neutrino Observatory detected a high-energy neutrino that arrived from the direction of the blazar TXS 0556. At the time, the blazar was undergoing a gamma-ray flare. This marked the first likely identification of a specific astrophysical source of high-energy neutrinos, opening a new window on the extreme physics in blazar jets. The detection provided strong evidence that blazars can accelerate protons to extremely high energies, not just electrons. When these protons collide with photons in the jet, they produce particles called pions, which decay into neutrinos. The neutrinos escape the jet and travel unimpeded across the universe, carrying information about the acceleration process. This connection between blazars and cosmic rays may be profound. For decades, astronomers have wondered where the highest energy cosmic rays come from. These particles have energies exceeding 10 to the 20th power electron volts, far higher than anything achievable in terrestrial accelerators. Blazars and their jets are now among the leading candidates for producing these ultra-high energy particles. By the 1980s, astronomers had identified a bewildering variety of active galactic nuclei. There were quasars, both radio-loud and radio-quiet. There were blazars with their extreme variability and featureless spectra. There were Seyfert galaxies, which resembled low-luminosity quasars in nearby spiral galaxies. There were radio galaxies with extended lobes but modest optical emission. Were these truly different types of objects, or were they the same phenomenon viewed from different perspectives? The answer that emerged, now known as the unified model of active galactic nuclei, is that viewing angle explains most of the observed diversity. The same basic engine, a supermassive black hole with an accretion disk and possibly jets, looks very different depending on whether you are looking at it face on, edge on, or somewhere in between. The key ingredient in this unification is a structure called the dusty torus. Surrounding the accretion disk at distances of roughly a light year from the black hole is a thick ring or donut of dusty gas. This torus is cool enough that dust grains can survive without evaporating, but its inner edge is heated by radiation from the accretion disk. The torus plays a crucial role in shaping what we see. If we view an active nucleus from above or below the torus, we see straight down to the central engine, the accretion disk, the high-velocity gas clouds near the black hole, and the broad emission lines are all visible. This is a Type 1 active nucleus, which includes quasars and Type 1 Seyfert galaxies. If we view the same object from the side, the torus blocks our view of the central engine. We cannot see the accretion disk directly. The high-velocity clouds near the black hole are hidden. We see only the larger-scale gas clouds further from the center, which produce narrower emission lines. This is a Type 2 active nucleus, including Type 2 Seyfert galaxies and narrow-line radio galaxies. The evidence for this geometric unification is substantial. When astronomers observe Type 2 objects in polarized light, they often detect the hidden Type 1 spectra. The central engine's light scatters off material above the torus and reaches us indirectly, revealing the broad emission lines that are blocked in direct viewing. Infrared observations also support the model. Type 2 objects show strong infrared emission from warm dust, exactly what you would expect if a thick dusty structure were absorbing optical and ultraviolet light from the central engine and re-radiating it at longer wavelengths. Adding jets to the picture extends the unification further. If jets are present and pointing toward us, we see a blazar. If the jets point perpendicular to our line of sight, we see a radio galaxy. Intermediate angles give intermediate properties. The full unified model thus explains most of the observed diversity of active galactic nuclei in terms of three variables: the luminosity of the central engine, the strength of the jets, and the viewing angle. Luminosity determines where an object falls on the scale from Seyfert galaxies to quasars. High luminosity objects are quasars, lower luminosity objects are Seyferts. This is primarily a function of the accretion rate onto the black hole. Jet strength determines whether an object is radio loud or radio quiet. This may depend on black hole spin, magnetic field structure, or the properties of the surrounding environment. Viewing angle determines the observed spectral type and whether the object appears as a normal active nucleus or a blazar. This unified picture is elegant and largely successful, but it is not complete. Some aspects of the observations do not fit neatly into the scheme. For example, the dusty torus is probably not a simple geometric structure. Real observations suggest that the obscuring material is patchy and variable, perhaps consisting of clouds rather than a smooth ring. The boundary between Type 1 and Type 2 viewing angles may be fuzzy rather than sharp. The relationship between jets and viewing angle is also more complex than a simple beaming story. Some objects that should appear as blazars based on their angles do not show the expected properties. Others that should not be aligned show blazar-like variability. There may also be intrinsic differences between objects that the unified model does not capture. Not all quasars may have the same underlying structure. The environment of the host galaxy, the history of the black hole's growth, and the current state of the fuel supply may all introduce variations. Despite these complications, the unified model remains the foundation for understanding active galactic nuclei. It explains why the same physical system produces such diverse appearances and allows astronomers to interpret observations in terms of intrinsic properties rather than apparent differences. The model also makes specific predictions that can be tested. The space density of different types of active nuclei should follow geometric relationships based on solid angles. Objects seen at different angles should have predictable relationships between their properties. Infrared emission from the torus should correlate with other measures of obscuration. These predictions have been largely confirmed, strengthening confidence in the unified picture. The diversity of active galactic nuclei, once bewildering, now appears as different faces of the same remarkable phenomenon. Matter falling into a supermassive black hole and releasing energy on a cosmic scale. The confirmation came through multiple independent lines of evidence. X-ray observations prove particularly powerful. X-rays from the innermost accretion disk can penetrate through modest amounts of obscuring material. By comparing X-ray properties with optical classifications, astronomers found exactly the pattern predicted by unification. Type 2 objects showed absorbed X-ray spectra, indicating material along the line of sight, while Type 1 objects showed unabsorbed emission. Spectropolarimetry provided some of the most compelling evidence. In 1985, astronomers Robert Antonucci and Joseph Miller observed the Type 2 Seyfert galaxy NGC 1068 using a technique that isolated polarized light. What they found was remarkable. Hidden within the polarized spectrum were the broad emission lines characteristic of Type 1 objects. The explanation was straightforward. Light from the hidden central engine was scattering off material above and below the obscuring torus. This scattered light was polarized, and it carried the spectral signature of the broadline region that direct viewing could not see. The Type 1 nucleus was there all along, simply hidden by geometry. Similar observations of other Type 2 objects revealed hidden Type 1 spectra in many cases. The unified model had made a prediction, and observations confirmed it. infrared interferometry has recently begun to resolve the dusty torus directly. Using baselines of hundreds of meters, astronomers can achieve angular resolution sufficient to measure the size and shape of the torus in nearby active nuclei. These observations reveal structures roughly consistent with the unified picture, though with significant complexity. The torus appears to be clumpy rather than smooth, consisting of individual clouds of dusty gas rather than a continuous medium. The inner edge of the torus, heated by radiation from the accretion disk, glows brightly at near-infrared wavelengths. The outer regions are cooler and emit primarily in the mid-infrared. The size of the torus scales with the luminosity of the central engine. More luminous nuclei have larger tori, presumably because the intense radiation pushes the inner edge of the dust distribution to greater distances. This relationship, called the size-luminosity relation, provides an independent check on the distances to active nuclei and has been used as a cosmological probe. The unified model also explains the relative numbers of different types of active nuclei. If the torus covers about half the sky as seen from the central engine, roughly half of all active nuclei should appear as type 1 and half as type 2. This is approximately what observations show, though the exact ratio varies with luminosity and redshift. For radio-loud objects, the situation is more complex. Blazars represent the small fraction of radio-loud active nuclei whose jets happen to point toward Earth. Given the typical opening angle of a few degrees, blazars should be outnumbered by radio galaxies by a factor of several hundred. This is consistent with observed number counts. The unified model has transformed how astronomers think about active galactic nuclei. Rather than cataloging an ever-growing zoo of apparently different objects, they now interpret observations in terms of a single underlying phenomenon. The question is no longer what kind of object is being observed, but what the viewing angle and intrinsic properties are. This shift in perspective has profound implications for understanding the cosmic evolution of black holes and galaxies. By combining observations of objects at all viewing angles, astronomers can construct complete pictures of the active nucleus population. They can measure the total energy output of black holes across cosmic time. They can study how activity correlates with galaxy properties, independent of the accidents of geometry. The unified model also predicts the existence of objects that should exist but are difficult to observe. For example, if a torus completely surrounds the central engine in some objects, blocking our view from all angles, these buried active nuclei would be invisible at optical wavelengths. They might reveal themselves only through X-rays energetic enough to penetrate the obscuring material, or through infrared emission from the heated dust. Searches for such heavily obscured active nuclei have indeed found them. Hard X-ray surveys, which detect the highest energy X-rays capable of piercing thick columns of gas, have revealed populations of active nuclei invisible to optical surveys. These buried sources may represent a significant fraction of all black hole accretion in the universe. Understanding these hidden populations is crucial for measuring the complete history of black hole growth. If a large fraction of accretion is obscured, optical surveys underestimate the total amount of matter consumed by black holes. The cosmic X-ray background, a diffuse glow of X-rays that pervades the universe, provides evidence that obscured accretion is indeed common. The spectrum of this background is best explained by the combined emission of large numbers of obscured active nuclei at various redshifts. The unified model has also guided the search for binary supermassive black holes. When galaxies merge, their central black holes should eventually sink to the center of the merged system and form a binary pair. Before they ultimately coalesce, the two black holes orbit each other, potentially producing distinctive observational signatures. Finding such binaries is challenging, but the unified model helps by predicting what signatures to look for. A binary in which both black holes are actively accreting might show two sets of emission lines at different velocities, or periodic variability as the orbital motion Doppler shifts the emission. Several candidate binary systems have been identified, though definitive confirmation remains elusive. The success of the unified model does not mean all questions are answered. Significant puzzles remain about the structure and origin of the key components. The torus itself is not well understood theoretically. What supports it against collapse? How does it form and evolve? Why does it have the size and covering factor that observations indicate? These questions connect to the broader issue of how gas flows through galaxies and feeds central black holes. The jets remain even more mysterious. Despite decades of research, the detailed mechanism by which jets are launched, accelerated, and collimated is not fully established. Whether jets are powered primarily by the accretion disk or by black hole spin is still debated. The conditions that determine whether a particular black hole produces powerful jets or remains radio quiet are poorly understood. The transition between Type 1 and Type 2 viewing angles is probably not as sharp as simple models suggest. Some objects show intermediate properties, as if they are viewed through patchy obscuration that partially reveals the central engine. Time variable obscuration, in which clouds move across the line of sight, has been detected in several objects, causing them to transition between Type 1 and Type 2 classifications over periods of months to years. These changing look active nuclei present a challenge to simple unification. If the classification changes on timescales short compared to any plausible structural evolution, something other than geometry must be involved. Perhaps the ionizing luminosity of the central engine varies, causing the broad line region to appear and disappear. Perhaps the torus structure itself changes on observable timescales. The unified model provides a framework, not a complete answer. It tells us that viewing angle matters and that different appearances do not necessarily indicate different underlying phenomena. But the details of the geometry, the physics of the components, and the evolution of the system over time remain active areas of research. What the unified model demonstrates above all is the power of a simple idea to organize a complex field. By recognizing that the same engine can look different from different angles, astronomers transformed a confusing menagerie into a coherent picture. The challenge now is to refine that picture, to understand the physics behind the geometry, and to connect the properties of active nuclei to the broader evolution of galaxies and the cosmos. One of the most valuable properties of quasars is that they can be seen at enormous distances. Because they are so luminous, they can be detected at redshifts where ordinary galaxies are too faint to observe. This makes them powerful probes of the early universe. The most distant quasar, known as of recent observations, has a redshift exceeding 7.5, meaning its light has been traveling for over 13 billion years. We see this object as it was less than 700 million years after the Big Bang, when the universe was only about 5% of its current age. This extreme distance creates problems as well as opportunities. The presence of billion solar mass black holes so early in cosmic history challenges our understanding of how black holes form and grow. Consider the timescale. The universe is about 13.8 billion years old. A quasar at redshift 7.5 is seen when the universe was 700 million years old. For a black hole to reach a billion solar masses by that time, it must have grown extraordinarily quickly. Even at the maximum possible rate, limited by the Eddington luminosity, a black hole doubles its mass only about every 40 million years. Starting from a stellar mass seed of 10 solar masses and growing continuously at the Eddington limit, the black hole would reach a billion solar masses in about 800 million years. The timeline is tight, but not quite impossible. However, the calculation assumes continuous maximum rate accretion with no interruptions, which seems unlikely. Any period of reduced accretion would slow the growth. The first black holes also needed time to form, further constraining the available growth time. These considerations have driven interest in alternative formation scenarios. Perhaps the first black holes did not start from stellar mass seeds, but from much larger initial masses. Direct collapse of primordial gas clouds to black holes of 10,000 solar masses or more would provide a substantial head start. The physics of direct collapse requires special conditions. Normally, gas clouds fragment into smaller pieces as they collapse, forming multiple stars rather than a single massive object. For direct collapse to occur, this fragmentation must be suppressed. One possibility involves the absence of heavy elements. The first gas clouds in the universe contained only hydrogen and helium, with no carbon, oxygen, or other elements that form from stellar nucleosynthesis. These heavy elements normally help gas cool efficiently, enabling fragmentation. Without them, cooling is less efficient, and larger masses can collapse without breaking apart. Another requirement is the presence of a strong ultraviolet radiation field. Photons of the right energy can dissociate hydrogen molecules, which are the primary coolant for primordial gas. If molecular hydrogen is destroyed faster than it can form, the gas cannot cool efficiently, and direct collapse becomes possible. These conditions might have existed in special environments in the early universe. A gas cloud collapsing near a young, luminous galaxy might be bathed in enough ultraviolet radiation to suppress fragmentation. If so, the cloud could collapse directly to a black hole of tens of thousands of solar masses, far larger than any stellar remnant. Theoretical models of this process produce what are called direct collapse black holes. These objects would be born large and could grow to supermassive scales in the available time without requiring impossibly efficient accretion. Direct observational evidence for direct collapse black holes remains elusive. By the time we observe quasars, their black holes have already grown to billions of solar masses, erasing evidence of their initial state. Detecting the collapse process itself would require observing at even higher redshifts, in the epoch before the first quasars turned on. Future telescopes may make such observations possible. The James Webb Space Telescope, designed to observe infrared light from the earliest cosmic epochs, can search for signatures of the first black holes and their host galaxies. If direct collapse black holes exist, their birth might produce distinctive observable signatures. Another possibility is that early black holes accreted faster than the Eddington limit. The Eddington limit assumes that radiation escapes spherically from the accreting object. If radiation can escape preferentially in certain directions, more matter can fall in from other directions without being pushed away. Super Eddington accretion might occur when the accretion rate is very high and the flow becomes geometrically thick. Under these conditions, photons can be trapped within the infalling material and advected into the black hole rather than escaping. The effective Eddington limit is increased, allowing faster growth. Evidence for super Eddington accretion comes from a class of objects called ultraluminous X-ray sources. These are compact objects in nearby galaxies that appear to exceed the Eddington limit for stellar mass black holes. While some are now known to be pulsars, others may indeed be accreting at super Eddington rates. Whether super Eddington accretion can persist long enough to grow billion solar mass black holes is uncertain. The process is inherently unstable, and strong outflows may limit how much mass actually reaches the black hole. Detailed simulations are beginning to explore these questions, but definitive answers remain elusive. The discovery of quasars at ever higher redshifts continues to push the timeline problem. Each new record-holding quasar, observed at an earlier epoch, requires even faster growth or earlier formation of the seed black hole. The current record holders already strain simple models of black hole growth. Beyond the formation question, high redshift quasars provide unique information about conditions in the early universe. Quasars at high redshift serve as background lights that illuminate the gas between them and us. This intergalactic medium contains hydrogen that absorbs light at specific wavelengths, creating absorption features in quasar spectra. At moderate redshifts, the Lyman alpha forest is visible, a series of narrow absorption lines caused by hydrogen clouds at different distances along the line of sight. Each cloud absorbs light at the same wavelength in its own rest frame, but the cosmic expansion shifts this absorption to different observed wavelengths. The pattern of absorption reveals the distribution and properties of intergalactic gas. At higher redshifts, beyond about 6, the absorption becomes so thick that it merges into a continuous blank region called the Gunn-Peterson trough. This indicates that the intergalactic hydrogen is no longer highly ionized. Before some redshift, the universe was filled with neutral hydrogen that absorbed virtually all light at these wavelengths. The transition from neutral to ionized hydrogen is called the epoch of reionization. After the Big Bang, The universe cooled enough for hydrogen atoms to form. These atoms were neutral and opaque to ultraviolet light. But within the first billion years, radiation from the first stars and quasars gradually ionized the intergalactic hydrogen, making the universe transparent again. Quasars play a crucial role in this story. Their intense ultraviolet emission ionized hydrogen across vast volumes of space, carving out bubbles of transparency in the neutral fog. As more quasars and galaxies formed, these bubbles expanded and merged until the entire universe was reionized. Observing quasars at and beyond the epoch of reionization tells us about this critical transition, the sharpness of the Gunn-Peterson trough, the statistics of transmitted flux, and the sizes of ionized bubbles all constrain when and how reionization occurred. Current evidence suggests reionization was largely complete by redshift 6, about 1 billion years after the Big Bang, but began as early as redshift 10 or higher. The contribution of quasars versus galaxies to the ionizing radiation remains uncertain. Early galaxies were more numerous, but quasars were more powerful individually. Recent observations have begun to measure the sizes of ionized bubbles around the highest redshift quasars. These proximity zones, as they are called, extend several million light-years from each quasar, regions where the quasar's radiation has ionized the surrounding hydrogen. The sizes of proximity zones provide information about how long the quasars have been shining. A quasar that just turned on will have a small proximity zone, while one that has been active for millions of years will have ionized a larger volume. These measurements indicate that high redshift quasars have typical lifetimes of at least 1 million years, consistent with expectations from accretion physics. Quasars at high redshifts also allow measurements of the metal content of intergalactic gas. Elements heavier than hydrogen and helium are produced by stars and dispersed into space by supernova explosions. Detecting these elements in the gas around early quasars reveals how quickly stars enrich the universe with heavy elements. Observations show that significant metal enrichment had already occurred by redshift 6, indicating that star formation was well underway in the first billion years. Some quasars show gas with nearly solar abundances of certain elements, suggesting that their host galaxies had already processed substantial amounts of material through stars. The hosts of early quasars are themselves interesting objects. Infrared and submillimeter observations reveal that many high redshift quasars are surrounded by large reservoirs of gas and dust and are actively forming stars at prodigious rates. These are among the most massive galaxies of their era, consistent with the idea that the most massive black holes form in the most massive systems. Star formation rates in these host galaxies can exceed 1,000 solar masses per year, hundreds of times higher than in the Milky Way today. This intense activity may be fueled by the same gas that feeds the central black hole. The connection between black hole growth and star formation is particularly tight in these early, rapidly growing systems. The relationship between quasar activity and galaxy formation in the early universe remains an active area of research. Did black holes form first and then build galaxies around them? Did galaxies form first and then grow black holes at their centers? Or did both processes occur simultaneously, each influencing the other? The answer seems to be the last option. The correlation between black hole mass and galaxy properties seen in the nearby universe suggests a connection that must have developed early. Understanding the nature of this connection requires studying both components at the earliest accessible epochs. The environments of early quasars provide additional clues. Several high redshift quasars have been found in regions with overdensities of galaxies, suggesting that they reside in the progenitors of present-day galaxy clusters. These protoclusters would have provided the dense environments necessary for rapid black hole growth. Mapping the large-scale environments of high redshift quasars is challenging but increasingly feasible. Wide-field surveys at infrared wavelengths can detect companion galaxies around distant quasars. These observations reveal that the most luminous quasars tend to live in the densest environments, as expected if massive black holes form preferentially in massive dark matter halos. The study of quasars in the early universe thus connects to some of the biggest questions in cosmology. How did the first structures form from the nearly uniform conditions after the Big Bang? What triggered the formation of the first stars and black holes? How did galaxies assemble their mass and develop the relationships between black holes and stellar populations that we observe today? Quasars, visible across most of cosmic history, provide a window into these processes. Each high redshift quasar is a signpost marking a site of intense activity in the young universe. By studying these objects, we trace the assembly of cosmic structure from its earliest stages. The energy released by quasars does not simply escape into the cosmos without effect. It interacts with the surrounding galaxy in ways that profoundly influence the galaxy's evolution. This interaction, called feedback, is now recognized as a crucial element in the formation and development of galaxies. The energy budget involved is enormous. A typical quasar produces about 10 to the power of 46 watts continuously for tens of millions of years. The total energy released over the active phase is comparable to the gravitational binding energy of an entire galaxy. If even a small fraction of this energy couples to the gas in the galaxy, the effects would be dramatic. Theoretical models of galaxy formation have long struggled with the problem. Simulations that include only gravity and gas physics predict galaxies that are too massive and form too many stars. Without some mechanism to suppress star formation, galaxies should have converted essentially all their gas into stars by the present day. Observations show this has not happened. Large galaxies contain far fewer stars than predicted. Much of their gas has either been prevented from cooling or has been expelled entirely. Something is suppressing star formation, particularly in the largest galaxies. Quasar feedback provides a natural explanation. The energy released by the central black hole heats the surrounding gas, preventing it from collapsing and forming stars. In extreme cases, the quasar can drive powerful winds that expel gas from the galaxy entirely, removing the raw material for future star formation. Two main channels deliver feedback energy from black holes to their host galaxies. The first is radiative feedback, sometimes called quasar mode. The intense radiation from the accretion disk heats surrounding gas and drives winds through radiation pressure. This mode is most important when the black hole is accreting rapidly and shining brightly as a quasar. The second channel is mechanical feedback, sometimes called radio mode or jet mode. Jets of relativistic particles deposit their energy far from the black hole, heating the surrounding medium and inflating large bubbles of hot plasma. This mode can operate even when the accretion rate is low, powered by the spin energy of the black hole. Observations have directly detected these outflows. Absorption lines in quasar spectra reveal gas moving outward at speeds of thousands of kilometers per second. In some cases, the absorbing gas is highly ionized, indicating that it has been energized by the quasar's radiation. In other cases, molecular gas has been detected in outflows, suggesting that even cold star-forming material is being expelled. The mass outflow rates can be extraordinary. Some quasars are driving outflows of hundreds of solar masses per year, far exceeding the rate at which the black hole is accreting. The energy and momentum in these outflows appear sufficient to unbind significant amounts of gas from the host galaxy. These fast outflows are often called ultra-fast outflows when observed in X-rays, where they appear as highly blue-shifted absorption lines from highly ionized iron. Velocities can reach 10 to 30% of the speed of light in extreme cases. The kinetic power carried by these outflows can approach the luminosity of the quasar itself, indicating highly efficient energy transfer. The outflows do not simply disappear. As they propagate through the galaxy, they sweep up ambient gas and drive large-scale structures. Observations with integral field spectrographs, which measure spectra across extended regions, have revealed galaxy-wide outflows stretching tens of thousands of light-years. These extended outflows show gas moving at hundreds to thousands of kilometers per second, far exceeding the escape velocity of the galaxy. The impact on star formation can be measured directly. Galaxies hosting the most powerful quasar outflows tend to have reduced star formation compared to similar galaxies without outflows. The effect is particularly pronounced in the central regions of galaxies, where the feedback is strongest. This connection between black hole activity and star formation provides a natural explanation for the observed correlations between black hole mass and galaxy properties. As the black hole grows, its feedback effects increase. Eventually, the feedback becomes strong enough to expel the gas needed for further growth, limiting both black hole accretion and star formation. The resulting self-regulation produces the tight correlations observed between black hole mass and stellar bulge properties. The jets provide another channel for feedback. As relativistic jets propagate through the galaxy and into the surrounding space, they deposit energy over large volumes. This energy heats the gas and inflates bubbles that can persist for hundreds of millions of years. Direct evidence for jet feedback comes from X-ray observations of galaxy clusters. The hot gas that fills clusters should cool and form stars at the cluster center. But observations show that cooling is suppressed. X-ray images reveal cavities in the hot gas, carved by jets from the central galaxy's black hole. The energy required to create these cavities is more than sufficient to offset the radiative cooling. The most famous example is the Perseus cluster, whose central galaxy, NGC 1275, hosts an active nucleus with jets. X-ray images reveal concentric cavities and ripples in the surrounding hot gas, evidence of repeated episodes of jet activity. The energy deposited over hundreds of millions of years has kept the cluster gas hot, preventing it from cooling and forming stars. Similar cavities have been detected in many galaxy clusters. Their prevalence indicates that jet feedback is a common phenomenon, operating in a significant fraction of massive galaxies. The total energy deposited by jets over cosmic time is sufficient to affect the evolution of the largest structures in the universe. The interplay between quasar mode and radio mode feedback may be important for understanding galaxy evolution. During the quasar phase, when the black hole is accreting rapidly, radiative feedback dominates. Winds driven by radiation pressure expel gas and suppress star formation. After the quasar fades, mechanical feedback from jets can maintain the suppression, preventing the gas from recooling. This combination may explain why the most massive galaxies are also the oldest and reddest. Their central black holes, having grown to enormous masses during early quasar phases, continue to suppress star formation through jet feedback. The galaxies cannot form new stars and gradually redden as their existing stellar populations age. The feedback process is self-regulating. When the black hole accretes rapidly, it produces powerful outflows that heat and disperse the gas supply. This reduces the fuel available for future accretion, causing the quasar to fade. As the galaxy's gas reservoir rebuilds, accretion can resume, triggering another episode of activity. This cycle may repeat multiple times over a galaxy's lifetime. Observations of nearby galaxies reveal multiple generations of cavities in the surrounding hot gas, evidence of repeated jet episodes. Each episode injects energy that delays the cooling and collapse of gas, maintaining the suppression of star formation. Computer simulations that include feedback from supermassive black holes produce galaxies that match observations much better than simulations without feedback. The most massive galaxies in these simulations have the right stellar masses, the right gas contents, and the right relationships between black hole mass and galaxy properties. The details of how feedback operates remain uncertain. How does energy from the accretion disk or jets couple to the surrounding gas? What fraction of the energy is thermalized versus kinetic? How do feedback effects depend on the properties of the black hole, the accretion rate, and the host galaxy? Different coupling mechanisms produce different outcomes. If feedback energy is deposited suddenly in a small region, it can drive strong shocks that expel gas efficiently. If energy is deposited gradually over large volumes, it may heat the gas gently without driving expulsion. The relative importance of these modes affects predictions for galaxy evolution. Observations are beginning to distinguish between these possibilities. Detailed studies of individual objects reveal the geometry and energetics of outflows. Statistical analyses of large samples constrain the overall impact of feedback on galaxy populations. Simulations with increasingly sophisticated physics can be tested against these observations. What is clear is that supermassive black holes are not passive objects that simply consume matter from their surroundings. They are active participants in galaxy evolution, injecting energy that shapes the properties of galaxies across the universe. The connection between black holes and galaxies, once thought to be coincidental, is now understood as a fundamental feature of cosmic structure formation. Quasars and the supermassive black holes that power them are not randomly distributed through space. They trace the large-scale structure of the universe, marking the locations of the most massive galaxies and the densest regions of cosmic matter. The universe on the largest scales is organized into a cosmic web of filaments, walls, and voids. Galaxies cluster along this web, with the richest clusters at the intersections of filaments. Dark matter, which outmasses visible matter by about 5:1, provides the gravitational scaffolding on which this structure forms. Quasars tend to be found in the densest environments, at least in the early universe. Their host galaxies were among the first to form and the fastest to grow. The abundance of gas in these regions provided fuel for both star formation and black hole accretion. Surveys of quasar positions have been used to map the large-scale structure of the universe out to billions of light years. Because quasars are so luminous, they can be detected at distances where galaxies are too faint to observe individually. The patterns in their distribution reveal the underlying structure of matter. The Sloan Digital Sky Survey, one of the largest astronomical surveys ever conducted, has catalogued over 500,000 quasars. Their three-dimensional distribution maps out the cosmic web across a significant fraction of the observable universe. The clustering of quasars on different scales provides information about the dark matter halos they inhabit and the cosmological parameters that govern structure formation. These surveys have confirmed the predictions of cosmological models. Quasars cluster on the scales expected from structure formation theory. Their distribution traces the cosmic web seen in simulations of dark matter evolution. The amplitude of clustering indicates that quasars reside in dark matter halos of roughly 10 trillion solar masses, corresponding to the most massive structures at their respective epochs. Quasars also provide a test of cosmological parameters. The relationship between redshift and distance depends on the expansion history of the universe, which in turn depends on the densities of matter, dark energy, and other components. By measuring the clustering of quasars as a function of redshift, astronomers can constrain these fundamental parameters. A particularly powerful technique uses baryon acoustic oscillations, sound waves that traveled through the early universe before it became transparent. These waves left a characteristic imprint on the distribution of matter, a preferred separation scale of about 500 million light-years. By measuring this scale in the clustering of quasars at different redshifts, astronomers can track the expansion history of the universe. Results from these studies have contributed to our understanding of dark energy, the mysterious component that causes the cosmic expansion to accelerate. The quasar data are consistent with a cosmological constant, as Einstein originally proposed, but the constraints are still being refined. A particularly powerful technique uses quasar absorption lines to probe the distribution of matter along the line of sight. The Lyman alpha forest, the series of absorption features caused by hydrogen clouds, effectively samples the density of matter at each point between the quasar and Earth. Statistical analysis of the Lyman alpha forest reveals how matter is distributed on different scales. The amplitude and shape of the fluctuations match predictions from the standard cosmological model with remarkable precision. This agreement provides some of the best evidence we have for the existence of dark matter and dark energy. The forest also constrains the properties of intergalactic gas. The temperature, density, and ionization state of the gas can be inferred from the detailed shapes of absorption lines. These measurements reveal that most baryonic matter in the universe resides not in galaxies but in the diffuse intergalactic medium, threading the cosmic web between galaxies. The Lyman alpha forest has been used to place limits on the mass of neutrinos, ghostly particles that barely interact with matter. Neutrinos contribute to the total matter density of the universe, but because of their high speeds, tend to smooth out small-scale structure. The observed amount of small-scale structure in the forest constrains how much mass neutrinos can have. Quasars also probe the distribution of matter through gravitational lensing. When light from a distant quasar passes near a massive foreground object, the gravitational field bends the light, distorting and magnifying the quasar image. In extreme cases, multiple images of the same quasar can appear around the lensing mass. Multiply-image quasars provide several kinds of information. The geometry of the images constrains the mass distribution of the lens. The time delays between images caused by different path lengths can be used to measure the expansion rate of the universe. The statistics of strong lensing constrain the abundance of massive structures along random lines of sight. Weak gravitational lensing, where the distortions are too small to produce multiple images but can be detected statistically, also uses background quasars. By measuring the slight distortions in quasar positions caused by foreground structure, astronomers can map the distribution of dark matter. The environments of quasars also reveal how black hole activity relates to galaxy evolution. Quasars at high redshifts are often found in protoclusters, the precursors of the massive galaxy clusters we see today. Their host galaxies are undergoing intense star formation, building the stellar masses that will characterize them at later times. This connection between quasar activity and environment may explain some puzzling observations. Quasars are most common at redshifts around 2, corresponding to the peak of cosmic star formation. Both phenomena may be driven by the same underlying cause, the abundance of gas in young, dense environments. As the universe ages, gas is consumed by star formation and expelled by feedback processes. The supply of fuel for both stars and black holes diminishes. Quasar activity declines, and the rate of star formation in the universe drops. By the present day, only a small fraction of galaxies host active nuclei, and these are typically less luminous than the quasars of the early universe. The decline of quasar activity is not simply a matter of fuel exhaustion. Galaxy mergers, which can funnel gas toward the central black hole, were more common in the past when galaxies were closer together. As the universe expands and galaxies spread apart, mergers become less frequent, and fewer black holes are triggered into activity. The large-scale environment affects quasar properties in other ways. The clustering of quasars depends on their luminosity, with more luminous quasars showing stronger clustering. This indicates that brighter quasars reside in more massive dark matter halos, consistent with the idea that black hole mass and halo mass are correlated. Radioloud and radioquiet quasars show different clustering properties. Radioloud quasars tend to be more strongly clustered, suggesting that jet production is related to halo mass or environment. This might be because more massive halos provide richer fuel supplies that can sustain the conditions necessary for jet launching. The environments of quasars thus tell a story of cosmic evolution. In the young universe, gas was abundant, and black hole activity was widespread. Over time, feedback and consumption depleted the gas supply. Mergers became rarer as expansion proceeded. The quasar phenomenon, so prominent in the early universe, gradually faded. Today's supermassive black holes are largely dormant, consuming only trickles of matter compared to their active past. But they remain at the centers of their galaxies, gravitational anchors that will persist for the lifetime of the universe. The energy they release during their active phases has left permanent marks on their host galaxies and the surrounding structures. Understanding the connection between quasars and large-scale structure requires combining observations across the electromagnetic spectrum with theoretical models of structure formation. The synthesis is still incomplete, but the outlines are clear. Black holes and their host halos grow together, shaped by the same processes of gas accretion and gravitational assembly. The cosmic web provides the framework within which this growth occurs, connecting the smallest and largest scales of the universe. The study of quasars and blazars has been transformed by advances in observational technology. Each new generation of telescopes has revealed features invisible to previous instruments, deepening our understanding of these extreme objects. Radio astronomy, which started the entire field, continues to advance. The technique of very long baseline interferometry, or VLBI, combines signals from telescopes separated by thousands of kilometers to achieve angular resolution impossible with any single dish. VLBI observations can resolve structures smaller than a light year in the cores of quasars and blazars. The most dramatic VLBI result came in 2019 with the first image of a black hole's shadow. The Event Horizon Telescope, a global network of radio telescopes operating as a single Earth-sized interferometer, observed the supermassive black hole at the center of the galaxy M87. The resulting image showed a bright ring of emission surrounding a dark central region, the shadow cast by the black hole's event horizon. This image confirmed decades of theoretical predictions. The ring corresponds to light emitted from hot gas swirling around the black hole and bent by the extreme gravitational field. The shadow marks the region from which no light can escape. The size and shape of these features match the predictions of general relativity with impressive precision. Observations of the Milky Way's central black hole followed in 2022. This black hole is smaller and less active than M87's, making the image technically more challenging. But the result again matched predictions, providing direct confirmation that the dark mass at our galaxy's center is indeed a black hole. Infrared astronomy has opened another window on active nuclei. The dusty torus that obscures the central engine in many sources radiates strongly in the infrared. Observations at these wavelengths reveal the torus structure, the temperature distribution, and the connection to the inner accretion disk. Adaptive optics on large ground-based telescopes has enabled infrared observations with angular resolution rivaling the Hubble Space Telescope. By correcting for the blurring effects of Earth's atmosphere in real time, adaptive optics systems can resolve details in the central regions of active galaxies that were previously inaccessible from the ground. These observations have begun to resolve the dusty torus directly in nearby active galaxies. Using infrared interferometry, which combines light from multiple telescopes, astronomers have measured the size and shape of the torus in several sources. The results confirm the general picture from the unified model, while revealing additional complexity. The torus turns out not to be a simple donut-shaped structure. It is clumpy, time variable, and may include outflowing material in addition to the static, obscuring medium. These details matter for understanding how the torus forms, evolves, and connects to the larger scale galaxy. X-ray astronomy provides the most direct view of the inner accretion disk. X-rays are emitted from the hottest material closest to the black hole, within a few event horizon radii. Variations in X-ray emission on timescales of hours to minutes probe the dynamics of this extreme region. The Chandra X-ray Observatory, launched in 1999, has provided high-resolution X-ray images of active nuclei for over 2 decades. Its observations have revealed the detailed structures of jets, mapped the hot gas in galaxy clusters, and detected obscured active nuclei invisible at other wavelengths. XMM Newton, a European X-ray mission, launched the same year, provides complementary capabilities with its large collecting area. It is particularly suited to spectroscopy, measuring the energies of individual X-ray photons with precision sufficient to detect emission lines from highly ionized ion. These ion lines are crucial diagnostics of the inner disk. Ion atoms near the black hole emit characteristic X-ray photons when illuminated by high-energy radiation. The detailed shape of these emission lines is distorted by the extreme gravitational field and high orbital velocities near the event horizon. Analysis of these distorted line profiles reveals the spin of the black hole and the geometry of the inner disk. Results indicate that many active nuclei contain rapidly spinning black holes, consistent with prolonged accretion from organized disks. The technique provides one of the few ways to measure black holes spin directly. NuSTAR, launched in 2012, extends X-ray observations to higher energies than Chandra or XMM Newton can reach. These hard X-rays can penetrate the obscuring material that blocks lower energy radiation, revealing heavily buried active nuclei invisible to other telescopes. NuSTAR has discovered populations of obscured black holes that contribute significantly to the cosmic X-ray background. Gamma-ray astronomy has opened yet another window on active nuclei, particularly blazars. The Fermi Gamma-ray Space Telescope, launched in 2008, surveys the entire sky at gamma-ray energies every few hours. It has detected over 3,000 blazars, providing a comprehensive view of the most extreme objects in the universe. Fermi's observations have revealed that blazars dominate the extragalactic gamma-ray sky. Their emission is highly variable, with some sources changing brightness by factors of 10 or more on timescales of hours. These rapid variations provide constraints on the size of the emitting region and the physics of particle acceleration in jets. The detection of gamma rays with energies exceeding 100 billion electron volts requires ground-based telescopes that observe the faint flashes of light produced when gamma rays hit Earth's atmosphere. Arrays of Cherenkov telescopes, including HESS in Namibia, MAGIC in the Canary Islands, and Veritas in Arizona, have detected dozens of blazars at these extreme energies. These very high-energy gamma rays challenge theoretical models. Photons of such high energy should interact with lower-energy photons and annihilate before escaping the source. The fact that they reach Earth constrains the density of photons in the emission region and the location where acceleration occurs. Multi-wavelength observations, combining data from radio through gamma-ray telescopes, are essential for understanding active nuclei. The emission at different wavelengths comes from different physical components and responds to changes at different rates. Only by tracking variations simultaneously across the spectrum can astronomers piece together the complete picture. Major campaigns have coordinated observations from dozens of telescopes to monitor individual blazars during outbursts. These efforts have revealed that flares at different wavelengths are not always correlated, indicating that multiple emission regions with different properties contribute to the total output. The detection of high-energy neutrinos from blazars in 2017 added a completely new dimension to these studies. Neutrinos, unlike photons, travel unimpeded through matter and radiation fields. The detection from astrophysical sources provides information unobtainable from electromagnetic observations alone. The IceCube Neutrino Observatory, a cubic kilometer of instrumented ice at the South Pole, detected a neutrino with energy of about 290 trillion electron volts arriving from the direction of the blazar TXS EO5E056. Simultaneous gamma-ray observations showed that the blazar was in a flaring state. This marked the first likely identification of a specific source of high-energy astrophysical neutrinos. Follow-up observations revealed evidence for earlier neutrino emission from the same source, suggesting that TXS 0506+056 is a persistent neutrino emitter. The implications are profound. If blazars produce high-energy neutrinos, they must be accelerating protons or other hadrons to extreme energies. The jets are not just streams of electrons, they contain a component of heavy particles capable of producing neutrinos through collisions with ambient photons. This opens the possibility that blazars are sources of ultra-high energy cosmic rays, the most energetic particles in the universe. The connection between jets, neutrinos, and cosmic rays is an active area of research that promises to revolutionize our understanding of particle acceleration in astrophysical environments. Gravitational wave astronomy, inaugurated by the detection of merging black holes in 2015, has not yet detected signals from supermassive black holes. But the pulsar timing arrays that monitor millisecond pulsars for tiny variations are beginning to detect hints of a gravitational wave background that may be produced by merging supermassive black hole binaries throughout the universe. If confirmed, this background would provide a new window on black hole mergers and the assembly history of massive galaxies. Future space-based gravitational wave detectors, like LISA scheduled for launch in the 2030s, will detect individual merging supermassive black hole binaries, allowing direct measurement of black hole masses and spins from gravitational waves. The James Webb Space Telescope, launched in December 2021, represents the next great leap in infrared capabilities. Its 6.5 meter mirror and location beyond Earth's orbit provide unprecedented sensitivity and resolution at infrared wavelengths. Early observations have already detected quasars at redshifts exceeding 10, pushing the frontier of the observable universe. Webb can study the host galaxies of high redshift quasars with detail impossible for previous telescopes. Its observations reveal the stellar populations, gas content, and morphologies of galaxies hosting the earliest black holes. These data constrain models of black hole formation and the coevolution of black holes and galaxies. The combination of all these observational capabilities, spanning the electromagnetic spectrum from radio waves to gamma rays and extending to neutrinos and gravitational waves, provides a comprehensive picture of active galactic nuclei. Each observing technique reveals different aspects of these complex systems. Together, they enable a unified understanding that no single method could achieve. After decades of accumulating evidence, the picture has become clear. The most luminous objects in the universe are powered by gravity at its most extreme, channeled through structures of astonishing complexity and violence. At the center of every quasar and blazar lies a supermassive black hole. These objects contain millions to billions of times the mass of our Sun, compressed into regions smaller than our solar system. Their gravitational fields are so intense that they bend spacetime itself, creating the conditions for the most efficient energy release in nature. Matter spiraling into these black holes forms an accretion disk. Friction within the disk heats gas to millions of degrees. The resulting radiation, produced in a region only light hours across, can outshine trillions of stars. This is the engine that powers quasars, visible across most of the observable universe. The efficiency of this engine is remarkable. Nuclear fusion, which powers stars, converts about 0.7% of mass into energy. Accretion onto a black hole can convert 6 to 40%, depending on the black hole's spin. This makes black hole accretion the most efficient, sustained energy source in the cosmos, exceeded only by matter-antimatter annihilation. The physics of accretion disks is complex and involves magnetohydrodynamic turbulence, radiation transport, and general relativistic effects. Simulations running on the world's largest supercomputers are only now beginning to capture the full complexity of these systems. The results match observations with increasing fidelity, validating our theoretical understanding. But the accretion disk alone does not explain all observations. The jets that emerge from some active nuclei require additional physics involving magnetic fields, rotation, and the extreme spacetime near the black hole. The launching mechanism for jets remains one of the outstanding problems in astrophysics. The Blandford-Zanayak process, which extracts energy from a spinning black hole through twisted magnetic field lines, provides a plausible explanation. But the details of how this energy is converted into the kinetic energy of relativistic particles are still being worked out. What we know is that the jets achieve velocities exceeding 99% of the speed of light. They remain collimated over distances millions of times their starting diameter. They carry power comparable to or exceeding the luminosity of the accretion disk. And they accelerate particles to energies far beyond what any human-built accelerator can achieve. The particles in the jets emit radiation through several processes. Synchrotron radiation, produced when electrons spiral in magnetic fields, dominates at radio through X-ray wavelengths. Inverse Compton scattering, where energetic electrons boost lower energy photons to high energies, produces gamma rays. And the detection of high-energy neutrinos indicates that hadrons, protons, or heavier nuclei are also accelerated in the jets. The unification of different types of active nuclei into a single picture represents a major intellectual achievement. Quasars, Safer galaxies, radio galaxies, and blazars are all manifestations of the same basic phenomenon, viewed from different angles or operating at different intensities. The dusty torus, the accretion disk, the jets, and the broadline region all fit together into a coherent picture. This unified model has predictive power. It tells us what we should observe when looking at active nuclei at different orientations. It explains the relative numbers of different types of objects. It predicts the existence of hidden populations that are now being discovered through X-ray and infrared surveys. The implications extend far beyond the active nuclei themselves. The feedback from accreting black holes shapes the evolution of galaxies. Energy injected by jets and winds suppresses star formation in massive galaxies, explaining why the largest galaxies are red and dead rather than blue and actively forming stars. The correlation between black hole mass and galaxy properties indicates a deep connection between the growth of black holes and the assembly of stellar mass. This connection must have been established early in cosmic history and maintained through subsequent evolution, understanding it requires combining observations of active nuclei, galaxy surveys, and theoretical models of structure formation. The earliest quasars pose a particular challenge. Black holes of 1 billion solar masses observed less than 1 billion years after the Big Bang require either exceptionally efficient growth or unusually massive seeds. The solution may involve direct collapse of primordial gas clouds, super Eddington accretion, or conditions in the early universe that do not exist today. Future observations will address these questions. The James Webb Space Telescope is finding quasars at ever higher redshifts, pushing into the epoch when the first black holes must have formed. Gravitational wave detectors may eventually hear the mergers of supermassive black hole binaries, providing direct evidence of black hole growth through mergers. The detection of gravitational waves from merging supermassive black holes would open an entirely new window on black hole physics. Unlike electromagnetic observations, which probe the environment around black holes, gravitational waves are emitted by the black holes themselves. They carry information about the masses, spins, and orbital dynamics of the merging system. Pulsar timing arrays are already detecting hints of a gravitational wave background at frequencies of nanohertz, corresponding to the orbital periods of supermassive black hole binaries. As sensitivity improves, individual sources may be resolved, allowing comparison with electromagnetic observations of active nuclei. The intellectual impact of understanding quasars and blazars extends across physics and astronomy. Black holes are natural laboratories for testing general relativity under extreme conditions. Jets are particle accelerators more powerful than anything humans can build. Active nuclei are tracers of cosmic structure visible across most of the universe's history. The journey from confusion to clarity has taken 6 decades. What began with unexplained spectral lines has led to an understanding of the most powerful sustained phenomena in the cosmos. The supermassive black holes that power quasars and blazars are now recognized as fundamental components of cosmic structure, essential for understanding the galaxies that harbor them. This understanding represents one of the great achievements of 20th and 21st century astronomy. It required the development of entirely new observational techniques, from radio interferometry to X-ray telescopes to gamma-ray observatories. It demanded theoretical advances in general relativity, plasma physics, and magnetohydrodynamics, and it benefited from computational power that allows simulations of black hole accretion with unprecedented detail. The result is a picture of the universe more extreme and more violent than anyone imagined a century ago. The brightest objects in existence are powered by the darkest. The fierce glow of quasars arising from matter's desperate plunge into the gravitational abyss. Despite remarkable progress, significant questions remain unanswered. These open problems drive current research and will shape the direction of the field for decades to come. The origin of supermassive black holes remains poorly understood. We see them in place by the first billion years after the Big Bang, but we do not know how they formed or grew to such enormous masses so quickly. Direct collapse, super Eddington accretion, and early mergers are all possibilities, but discriminating between them requires observations of even earlier epochs. The mechanism that launches relativistic jets is still debated. We know that magnetic fields are essential, and that the jets can extract energy from either the accretion disk or the spinning black hole. But the detailed physics of how magnetic energy is converted into kinetic energy of relativistic particles has not been fully worked out. The distinction between radio-loud and radio-quiet quasars lacks a complete explanation. About 10% of quasars produce powerful jets while the majority do not. Black hole spin is a likely factor, but it cannot be the whole story. The structure of the magnetic field, the properties of the accretion flow, and the environment of the host galaxy may all play roles. The variability of active nuclei contains information about the structure and dynamics of the central engine, but extracting this information requires sophisticated analysis techniques. The transfer of energy through the disk, the launching of individual blobs into the jet, and the response of surrounding gas to changes in ionizing radiation all produce variations on different timescales. Reverberation mapping has become a powerful tool for measuring black hole masses, but the technique requires long-term monitoring campaigns and careful analysis. Current facilities are mapping hundreds of active nuclei, building statistical relationships between measurable properties and fundamental parameters like mass and accretion rate. The coevolution of black holes and galaxies is now firmly established, but the mechanisms that connect them are still being explored. How does feedback energy couple to the surrounding gas? How does the coupling depend on the properties of the black hole and the host galaxy? How does the relationship change with cosmic time? These questions require multi-wavelength observations combined with theoretical models. Current surveys are measuring the properties of active nuclei and their hosts across cosmic time, from the local universe to redshifts beyond 7. The statistical relationships emerging from these surveys constrain models of black hole and galaxy evolution. The role of active nuclei in ionizing the universe remains uncertain. Quasars produce copious ionizing radiation, but they may be too rare to dominate the ionizing budget. Galaxies are more numerous, but individually less powerful. The relative contributions depend on the abundance of faint active nuclei at high redshift, which current surveys are beginning to constrain. The connection between jets, neutrinos, and ultra-high energy cosmic rays is a new frontier opened by the ice cube detection. If blazars are major sources of high-energy neutrinos, they may also be responsible for a significant fraction of the cosmic ray flux at the highest energies. Testing this hypothesis requires coordinated observations across the electromagnetic spectrum and continued monitoring for neutrino emission. Machine learning is transforming how astronomers analyze the massive datasets produced by modern surveys. Algorithms can classify objects, identify rare phenomena, and extract patterns from data too vast for human inspection. These techniques are being applied to quasar identification, variability classification, and the search for unusual objects. New facilities under construction or planning will address many current limitations. The Vera C. Rubin Observatory, expected to begin operations soon, will survey the entire southern sky repeatedly for a decade, discovering millions of new active nuclei and tracking their variability. The Square Kilometre Array, a radio observatory being built in Australia and South Africa, will revolutionize our view of the radio sky with unprecedented sensitivity and resolution. Space missions continue to push boundaries. The James Webb Space Telescope is already transforming our understanding of high redshift quasars and their host galaxies. Future X-ray missions with larger collecting areas and better spectral resolution will probe the inner accretion disk in greater detail. Proposed gamma-ray telescopes will extend the energy range and improve the angular resolution of current instruments. The detection of gravitational waves from supermassive black hole mergers, expected within the next decade from pulsar timing arrays, and eventually from space-based detectors like LISA, will provide an entirely new perspective on black hole growth and evolution. The field remains vibrant precisely because so many questions remain open. The physics of extremes, where gravity is strongest, matter is hottest, and accelerations are greatest, continues to reveal surprises. Each new observational capability has discovered phenomena that challenged existing understanding and required theoretical innovation. The study of quasars and blazars has matured from a confusing puzzle into a coherent scientific discipline, but it has not reached a final answer. The universe still holds secrets in the hearts of galaxies, and astronomers continue the work of uncovering them. We have traveled from the confused spectral lines of 1963 to the direct images of black hole shadows in 2019 and beyond. Along the way, we have witnessed one of the great scientific detective stories of the modern era. When Martin Schmidt recognized the enormous redshift of 3C273, he could not have imagined where that discovery would lead. The objects he revealed to the world turned out to be powered by supermassive black holes, entities that seemed like mathematical curiosities when Einstein's equations first predicted them. These black holes are not merely exotic objects at the margins of physics. They are central features of cosmic architecture, present at the heart of every major galaxy. The energy released by quasars defied explanation for years. No known process could produce such luminosity from such a small region. The solution required embracing the most extreme predictions of general relativity and recognizing that gravity itself, the weakest force in everyday experience, becomes the most powerful energy source in nature when matter falls toward a black hole. The jets that stream from active nuclei at nearly the speed of light challenged and continue to challenge our understanding of plasma physics and particle acceleration. They create structures spanning millions of light years, depositing energy that shapes the evolution of galaxies and clusters. They accelerate particles to energies beyond anything achieved by human technology, making them natural laboratories for studying physics at its extremes. The unified model that brings together quasars, Seyfert galaxies, radio galaxies, and blazars represents a triumph of scientific reasoning. What appeared to be a confusing zoo of different objects turned out to be the same basic phenomenon viewed from different perspectives. The insight that geometry matters as much as intrinsic properties transformed the field. The connection between black holes and galaxies has profound implications for understanding cosmic structure. Black holes are not passive bystanders in galaxy evolution. They are active participants whose feedback shapes the properties of their hosts. The correlations between black hole mass and galaxy properties testify to a deep connection established early in cosmic history and maintained through billions of years of subsequent evolution. Quasars visible at the edge of the observable universe tell us about conditions when the cosmos was young. They reveal the rapid growth of massive structures, the enrichment of the intergalactic medium with heavy elements, and the transition from neutral to ionized hydrogen that made the universe transparent. They serve as background lights whose spectra encode information about everything between them and us. The study of these objects has required and driven technological innovation. Radio astronomy, X-ray astronomy, gamma-ray astronomy, and gravitational wave astronomy all find natural applications in studying active nuclei. Each new wavelength regime has revealed phenomena invisible to previous techniques. The most recent example, the detection of high-energy neutrinos from blazars, opens yet another window on extreme astrophysical processes. What does the future hold? New telescopes will discover quasars at ever earlier times, probing the epoch when the first black holes formed. We may finally understand whether these objects grew from stellar remnants or from direct collapse of primordial gas. We may detect the gravitational waves produced when supermassive black holes merge, witnessing directly the growth of these cosmic giants. Better simulations will capture the physics of accretion and jet launching with increasing fidelity, allowing detailed comparison with observations. Machine learning will identify patterns in the vast datasets produced by sky surveys, revealing populations of objects we do not yet know to look for. The questions that remain unanswered today will yield to persistent investigation, as the questions of 1963 have yielded over the intervening decades. But science does not merely answer questions, it reveals new ones. Each advance opens fresh mysteries, inviting the next generation of astronomers to continue the exploration. What we can say with confidence is that the universe contains phenomena far more extreme than the everyday world suggests. The gentle glow of stars, the patient turning of galaxies, the slow expansion of space, all of these familiar features coexist with violence beyond imagination. At the centers of galaxies, matter falls into oblivion and releases its gravitational energy in the brightest displays nature produces. These objects are not separate from the cosmos we inhabit. The supermassive black hole at the center of our own Milky Way, now directly imaged, is the dormant remnant of past activity. The energy released by our black hole when it was young shaped the galaxy we live in. We are connected through the physics of gravity and gas and light to the most extreme phenomena in existence. The story of quasars and blazars is ultimately a story about the universe revealing its nature to patient observers. For thousands of years, humans looked at the sky and saw lights. In the last century, we learned to see beyond visible light, to hear the radio whispers and gamma-ray screams of the cosmos. We discovered that the universe is more dynamic, more violent, and more strange than anyone imagined. This discovery continues. The brightest objects in existence still hold secrets. The black holes that power them still pose fundamental questions about gravity, matter, and energy. The jets they produce still challenge our understanding of particle physics and plasma dynamics. The role they play in shaping galaxies still requires elucidation. What remains is the work of science: to observe, to theorize, to test, and to revise. The tools are better than ever. The questions are sharper than ever. The potential for discovery has never been greater. In the hearts of distant galaxies, matter spirals toward its final fate. Light escapes and travels for billions of years to reach our telescopes. We capture that light and decode its message. And in doing so, we learn something profound about the universe that created us and the processes that govern it. That quasars and blazars, the brightest objects in existence, illuminate more than the cosmos. They illuminate our capacity to understand, to wonder, and to persist in the face of mystery. That capacity, as much as the objects themselves, is what this documentary has celebrated. The universe is extreme, and we are here to witness it.